Welcome to our walkthrough of LeetCode problem number 1898, maximum number of removable characters. In this session, we'll explore the problem, break down key concepts, and analyze efficient approaches to solve it. Let's get started. In this problem, we are given two strings, s and p. The string p is a subsequence of s, meaning that p can be formed by deleting some characters from s without rearranging the remaining ones. Additionally, we are provided with an array called removable, which specifies the indices in S where we are allowed to remove characters. The task is to determine the maximum number of indices from the removable array that we can remove from S while ensuring that P remains a subsequence of the modified version of S. The goal is to maximize the number of characters we can remove without breaking this subsequence condition. The input consists of three key elements: the string S, the subsequent string P, and the array removable. The output is a single integer representing the maximum number of indices that can be removed while preserving P as a subsequence. Let's look at an example to understand this better. Suppose S is equal to abcac, P is ab, and the removable array is 3, 1, 0. We start by removing characters in the order specified by removable. First, we remove the character at index 3, which modifies S from abcac to abcb. Here, P equals ab is still a valid subsequence. Next, we remove the character at index 1, changing S to acb. Again, P equals ab remains a subsequence. However, if we remove the character at index 0, S becomes CCB, and now P equals ab is no longer a subsequence. Therefore, the maximum number of removable characters in this example is 2. In another example, let S equal abcd, P equal ABCD, and the removable array be 3, 2, 1, 4, 5, 6. Here, we begin by removing the character at index 3, which transforms S into abded. The subsequence P equals ABCD is still valid. However, if we proceed to remove the character at index 2, the modified S becomes add, and P equals ABCD is no longer a subsequence. In a third example, if S is abcab, P is ABC, and removable is 0, 1, 2, 3, 4, we will analyze the result in the next part. This means the maximum number of removable characters in this case is 1. For the third example, removing any character from S immediately breaks the subsequence condition for P equals ABC. For instance, removing the first character changes S to cab, but now P equals ABC is no longer a subsequence. Since no characters can be removed without violating the condition, the maximum number of removable characters is 0. This demonstrates the importance of carefully checking how each removal affects the subsequence condition. To summarize, there are several constraints and edge cases to consider for this problem. The string S and P consist only of lowercase English letters, and the removable array is a permutation of indices in S. Edge cases include scenarios like having no removable characters, where the result is 0, or when P is an empty string, which is always a subsequence, allowing you to remove all characters specified in removable. Additionally, the solution needs to handle large input sizes efficiently, as the lengths of S, P, and removable can reach up to 100,000. These constraints highlight the need for an optimized approach to solve the problem effectively. To tackle problem number 1898, we begin by examining a straightforward yet inefficient brute force approach. The intuition here is simple: we remove characters from the string S, one at a time, following the order specified in the removable array. After each removal, we check if the string P still remains a subsequence of the modified S. The implementation involves iterating through the removable array, simulating each character removal, and using a helper function to validate whether P is still a subsequence. However, the major drawback is its inefficiency. Subsequence validation for each removal takes O(n), where n is the length of S, and repeating this for all m elements and removable results in a total complexity of O(m*n). Given that m can go up to 10 to the power of 5, this approach quickly becomes computationally prohibitive for large inputs, making it unsuitable in practice. Instead, we turn to a more optimized strategy that combines binary search with subsequence validation. This approach is built on key observations. First, the problem essentially asks us to find the maximum number of characters we can remove while ensuring P remains a subsequence of S. This can be reframed as a decision problem, For a given k, is p still a subsequence after removing the first k characters specified in removable? By solving this decision problem efficiently, we can use binary search to determine the maximum valid k. The method involves iterating through the range 0, m, where m is the size of removable, and using binary search to narrow down the largest feasible k. For a given k, we simulate the removal of the first k characters by marking them as deleted using a mask array. We then validate if p remains a subsequence of the modified s. The complexity of this approach is significantly better. Binary search requires O log m iterations, and subsequence validation for each iteration takes O n. This results in an overall complexity of O n log m, which is highly efficient even for large inputs. This optimized approach is chosen because it effectively balances efficiency, scalability, and clarity. The key insight lies in reframing the problem as a decision problem, allowing us to leverage binary search for an elegant solution. By combining binary search with a helper function for subsequence validation, we avoid the inefficiencies inherent in brute force methods while ensuring correctness. Comparing the two strategies highlights the trade-offs. The brute force method is simpler to implement but computationally expensive, with a complexity of O m n. Meanwhile, the binary search approach, though slightly more complex to implement, achieves an efficient O n log m complexity, making it well suited for large inputs. Other alternatives, such as dynamic programming, are unnecessary here because the problem structure allows for a more direct and efficient solution. Overall, the chosen strategy provides the best balance between performance and simplicity, making it the optimal choice for this problem. In this problem, we aim to determine the maximum number of characters that can be removed from the string s, following the order specified by the removable array, while ensuring that p remains a subsequence of the modified version of s. A subsequence is formed by deleting 0 or more characters from a string without changing the order of the remaining characters. To solve this efficiently, we use a binary search combined with a two-pointer approach to check for subsequences. The key idea here is to binary search for the maximum value of k, where k represents the number of removable characters, such that p still remains a subsequence of the resulting string. To do this, we start by defining the binary search range from 0 to the length of the removable array. For each candidate value of k, we temporarily remove the first k characters from s as specified by the removable array and check whether p remains a subsequence of the modified string. This process allows us to efficiently narrow down the maximum valid k that satisfies the condition. The next step is to implement a helper function, is_subsequence, which determines if p is a subsequence of a given string. This is done using a two-pointer approach. One pointer, I, iterates through the string s, while another pointer, j, iterates through p. Whenever the current characters of s and p match, both pointers are advanced. If the pointer for p, j, reaches the end of the string, we know that p is a subsequence, and the function returns true. Otherwise, it returns false. To account for the removal of characters, we modify this function to skip any indices in s that are marked as removed. With this helper function in place, we can proceed to the main binary search implementation. We initialize the binary search range with low set to 0 and high set to the length of the removable array. For each midpoint, mid, we simulate the removal of the first mid characters from s based on the removable array and use is_subsequence to check if p remains a subsequence. If p is still a subsequence, it means we can try removing more characters, so we set low to mid plus 1. Otherwise, we reduce the number of removable characters by setting high to mid 1. Lastly, we account for edge cases. If p is empty, it is always a subsequence, so we can remove all characters. If s is empty but p is not, p cannot be a subsequence, so the result is 0, and we ensure that indices in removable are valid for s. The binary search approach is particularly efficient because it avoids the need to check every possible value of k, which would result in a brute force time complexity of O n squared. Instead, binary search narrows down the range of k and O log len removable iterations. Combined with the two-pointer subsequence check, which operates in O n time, the overall complexity becomes O n asterisk log len removable. Key insights that make this method efficient include the use of a Boolean array to simulate character removal. This array marks the indices to be skipped during the subsequence check, allowing us to dynamically handle removals without modifying the string itself. Additionally, the two-pointer technique ensures that the subsequence check is linear in time complexity, which is crucial for maintaining efficiency. By combining binary search, the two-pointer approach, and optimized data structures like the Boolean array, we achieve a solution that balances clarity and performance, making it well-suited for the problem at hand. This code solves LeetCode problem number 1898, maximum number of removable characters, using binary search combined with a subsequence validation function. The function maximum removals calculates the maximum number of characters that can be removed from string S such that P remains a subsequence of S. First, the helper function is _subsequence checks if P is a subsequence of a modified version of S, or indices in the removed underscore set have been ignored. This is achieved using a two-pointer technique. One pointer traverses S, and the other traverses P. If characters match and the index is not removed, the pointer for P advances. The function returns true if all characters of P are matched. The main function uses binary search to determine the maximum number of removable characters. The left and right pointers define the search range, starting from 0 to the length of removable. The midpoint, mid, represents the number of characters to test for removal. A set of removable indices up to mid is created and passed to as underscore subsequence. If P remains a subsequence after these removals, the result is updated, and the search continues in the upper half of the range. Otherwise, the search focuses on the lower half. The function returns the maximum number of removable characters found during the binary search. This approach ensures efficiency, with a time complexity of O, n asterisk log m, where n is the length of S and m is the length of removable. This is because the subsequence check runs in linear time, and the binary search executes in logarithmic time relative to the size of removable. Here, we begin by defining the maximum removals method, which takes three inputs, the string S, the string P, and an array removable. The goal is to determine the maximum number of removable characters from S such that P remains a subsequence of S. We initialize two pointers, left and right, to perform a binary search over the number of removable characters, starting with the range from 0 to the length of the removable array. The variable result will hold our final answer. Inside the while loop, we calculate the midpoint mid of our binary search range. For each value up to mid, we add the corresponding index from the removable array to a set called removed set. This set represents the indices of characters that are temporarily considered removed from S. We then check if P is still a subsequence of S with these characters removed by calling the helper method isSubsequence. If it is, we update result to mid and shift the left pointer to explore larger values. Otherwise, we adjust the right pointer to look for smaller values. Finally, we return the result after the binary search completes. The helper method isSubsequence checks whether P is a subsequence of S, considering the indices in removed set as removed. We use two pointers, I and j, to traverse S and P, respectively. While iterating through S, we skip over any indices that are in removed set. If the current character in S matches the current character in P, we increment the pointer j to check the next character in P. The pointer I is always increment to move through S. Once the loop ends, we return whether j has reached the length of P, which would mean that all characters in P were successfully matched in order within S. This method ensures that we efficiently verify the subsequence condition for the given set of removed indices. Here, we start with a simple example where the string S is abcac, the pattern P is ab, and the removable indices are 3, 1, 0. We initialize our binary search with left set to 0, right set to 3, which is the length of the removable array, and result initialized to 0. The binary search begins by calculating the midpoint mid as 0 plus 3, // 2 equals 1. At this step, we remove only the first index in removable, which is index 3, resulting in the set 3. Now, we check if P is still a subsequence of the modified string S. As we trace through the characters, we find that S0 matches P0 and S1 matches P1. This confirms that P remains a subsequence, so we update result to 1 and move the left boundary to 2 to explore more removable indices. Next, we compute mid equals 2 plus 3 // 2 equals 2, meaning we now remove indices 3, 1, resulting in the set 1, 3. Again, we check if P is a subsequence by tracing through the modified string S. Here, S0 matches P0 and S2 matches P1. Since P is still a subsequence, we update result to 2 and adjust left to 3 for the next step. With left now at 3, we calculate mid equals 3 plus 3 / 2 equals 3. This time, we remove all indices in removable, which are 3, 1, 0, resulting in the set 0, 1, 3. We then check if P is still a subsequence of the modified string S. Tracing through the characters, we see that S2 does not match P0, which means P is no longer a subsequence. As a result, we update right to 2, which effectively ends the binary search since left is greater than right. The final value of result remains 2, indicating that we can remove up to 2 characters from S while still keeping P as a subsequence. The output for this example is 2. Now, let's consider an edge case where the removable array is empty. Here, the string S is ABC, the pattern P is also ABC, and removable is an empty list. Since there are no indices to remove, we initialize left, right, and result all to 0. The binary search begins, and with mid equals 0 plus 0 / 2 equals 0, we attempt to remove the first 0 indices from removable, resulting in an empty set. Checking if P is a subsequence of S, we trace through the characters and find that S0 matches P0, S1 matches P1, and S2 matches P2. This confirms that P is indeed a subsequence, so we update result to 0 and increment left to 1. However, since left now exceeds right, the binary search ends, and the final result remains 0. This means no characters need to be removed to keep P as a subsequence. The output for this example is 0. In this more complex example, the string S is abcac, the pattern P is ABC, and the removable indices are 1, 3, 5, 0. We begin with left set to 0, right set to 4, and result initialized to 0. First, we compute mid equals 0 plus 4 / 2 equals 2, so we remove the first 2 indices in removable, which are 1, 3, resulting in the set 1, 3. Now, we check if P is a subsequence of the modified string S. Tracing through, S0 matches P0, S2 matches P1, and S4 matches P2. Since P remains a subsequence, we update result to 2 and move left to 3. Next, we compute mid equals 3 plus 4 / 2 equals 3 and remove indices 1, 3, 5, resulting in the set 1, 3, 5. Once again, we check if P is a subsequence. When removing the indices 1, 3, 5, we trace through the modified string S and find that S0 matches P0, S2 matches P1, and S4 matches P2. This shows that P is still a subsequence, so we update result to 3 and adjust left to 4. Finally, we compute mid equals 4 plus 4 / 2 equals 4 and remove all indices in removable, which are 1, 3, 5, 0, resulting in the set 0, 1, 3, 5. At this point, we trace through the modified string and find that S2 does not match P0, meaning P is no longer a subsequence. We update right to 3, ending the binary search since left exceeds right. The final value of result is 3, indicating that up to 3 characters can be removed while keeping P as a subsequence. The output for this example is 3. To analyze the time complexity of the maximum removals function, we need to consider how the binary search and the is_subsequence helper function work together. Binary search operates over the range of indices in the removable array, which contains k elements. Since binary search divides this range in half at each step, it performs O log k iterations. For each midpoint during the binary search, we check if P remains a subsequence of S after removing the first mid indices in removable. This involves 2 sub-operations. First, converting the first mid elements of removable into a set, which takes O, mid, time, and second, traversing both S and P to verify the subsequence condition, which takes O, n plus m, time, where n and m are the lengths of S and P. These 2 operations together contribute to the overall time complexity of the function. Now, we can compute the total time complexity. For each iteration of the binary search, we perform the is_subsequence check. The cost of building the set for removable indices is O, mid, which is bounded by O, k, since mid can go up to k. The subsequence check adds O, n plus m, resulting in an overall cost of O, k plus n plus m, per iteration. Since binary search runs for O, log k, iterations, the total time complexity becomes O, k plus n plus m, asterisk log k. In the worst-case scenario, if k is close to n, the complexity simplifies to O, n asterisk log k, assuming k dominates m. This logarithmic scaling with respect to k is what makes the binary search approach efficient for large input sizes. Next, let's look at the space complexity. The is_subsequence helper function uses a set to store the removed indices, and the size of this set is at most k, which means it requires O, k, additional space. The binary search itself only uses a few constant variables, such as left, right, mid, and result, which together take O, 1, space. On the input side, the strings s and p occupy O, n, and O, m space, respectively, while the removable array uses O, k space. Combining these, the total space complexity is dominated by the set used in is_subsequence and the input storage, leading to an overall space complexity of O, n plus m plus k. This ensures that the space usage remains manageable even for larger inputs. To better understand the efficiency of the optimized approach, let's compare it to a naive brute force method. In the naive approach, we would iteratively remove every possible subset of indices from removable and check if P remains a subsequence of S. Since there are 2 to the power of k subsets, and each subsequence check takes O, n plus m, time, the total time complexity of the brute force method is O, n plus m, asterisk 2 to the power of k. This exponential growth makes it infeasible for large values of k. On the other hand, the optimized approach uses binary search to limit the number of subsequence checks to O, log k. Each check still takes O, k plus n plus m, giving a total time complexity of O, k plus n plus m, asterisk log k. The table here summarizes the difference, showing that the optimized approach is significantly faster while maintaining the same space complexity of O, n plus m plus k. The key takeaway is that the optimized approach is exponentially faster than the brute force method for large k, thanks to the efficiency of binary search and the reduced number of is_subsequence checks. Looking at the best, average, and worst cases, the time complexity remains the same at O, k plus n plus m, asterisk log k, because the binary search always involves at most log k iterations. However, in practice, the best case may involve fewer iterations if the solution space is small. The average case assumes a balanced distribution of iterations, while the worst case involves traversing all log k iterations and fully processing S and P during each subsequence check. Regardless of the scenario, the space complexity remains consistent at O, n plus m plus k, ensuring that the approach is both time efficient and memory efficient for large inputs. A common mistake in this problem is neglecting to validate whether the subsequence relationship between P and S is preserved after removing characters according to the removable array. Simply assuming the relationship remains intact can lead to incorrect results, especially if characters are removed in the wrong order. To avoid this, you should verify the subsequence condition after each removal. A more efficient way to handle this is by using a binary search approach to systematically test validity without unnecessary checks. Another pitfall is implementing a brute force solution where you iteratively remove characters and check the subsequence condition for every prefix of removable. This approach is highly inefficient, with a time complexity of O, k asterisk n, and becomes impractical for large inputs. Instead, binary search can optimize this process significantly. Lastly, even with binary search, errors can arise from mishandling edge cases, such as when no characters or all characters in removable can be removed. To avoid issues like infinite loops or off-by-one errors, ensure your binary search includes proper boundary checks and termination conditions. Another issue arises when the problem statement is misunderstood, particularly when removing characters is confused with reordering or modifying the string S. The problem explicitly requires that characters be removed in the order specified by the removable array, and not arbitrarily. Misinterpreting this constraint can lead to entirely incorrect solutions. Take the time to carefully read and understand the problem requirements before diving into implementation. Additionally, overlooking edge cases is a common oversight. For example, failing to test scenarios where P is empty, removable is empty, or S does not contain P at all can lead to flawed assumptions about the initial validity of P as a subsequence. To ensure your solution is robust, explicitly test these edge cases and verify that your logic handles them appropriately. When approaching this problem in an interview setting, it's crucial to identify the key constraints early on. Understanding the relationship between the subsequence condition and the removable array is vital, as it helps you recognize that binary search is the optimal approach here. While brute force solutions can be a helpful starting point for brainstorming, they're not practical for large inputs. Transitioning to an optimized approach, such as binary search combined with a helper function to validate subsequences, will save valuable time. Additionally, clear communication is essential. Make sure to articulate your thought process when validating the subsequence condition and explain how you're addressing edge cases. Finally, demonstrate your awareness of time complexity. Highlight the inefficiency of naive approaches with O(k*n) complexity and emphasize the improvements gained by using binary search, which reduces complexity to O(k*(log)n). This shows both problem-solving skill and a focus on optimization. To build a strong foundation for this problem, it's helpful to explore related problems. For instance, LeetCode 392 is subsequence, focuses on the core concept of validating subsequences and is an excellent prerequisite. LeetCode 792, number of matching subsequences, extends this idea to multiple queries, emphasizing efficient validation techniques. Another useful problem is LeetCode 1717, maximum score from removing substrings, which involves optimization strategies for removing substrings to maximize a score. Lastly, LeetCode 673, number of longest increasing subsequences, highlights dynamic programming approaches for handling subsequences with specific constraints. Studying these problems will deepen your understanding of subsequence validation and optimization, and provide valuable insights that can be applied to this problem. There are several alternative approaches to solving this problem, each with its own trade-offs. The most efficient method is using binary search with a helper function. This approach balances clarity and performance, reducing the overall complexity to O(k*(log)n). With binary search, you can systematically determine the maximum number of removable characters while validating the subsequence condition at each step. Another option is the two-pointer approach, which is simpler to implement but less efficient for large inputs. This method involves iteratively validating subsequences for each prefix of the removable array. Finally, you can use optimized validation with hashing, which speeds up subsequence checks by leveraging a hash set to store indices of removable characters. While this approach requires additional memory, it can significantly reduce the time needed to validate subsequences, making it a viable alternative for certain scenarios. Great job following along. Today, we analyzed the maximum number of removable characters problem, discussed key strategies, and highlighted important takeaways. Don't forget to practice similar problems to reinforce your understanding. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!